All right, so let's now look at motion in gravitational fields. So, how does the force of gravity determine the motion of planets and satellites? So this is like the more content part of module 5. So, definition then. Orbital motion is a uniform circular motion of an object whereby the centripetal force is provided by gravity. So we can use this to find orbital velocity as well, which is the minimum velocity required. The minimum velocity required for an object to orbit a planetary body, or an object to orbit a planet, for example. So within this, within these two equations, we have u is equal to negative gmm over r, that is gravitational potential energy, and F is equal to gmm over r squared. So in this case, r is the distance from the center of the mass, and r is an altitude is equal to, so yeah, r in this case is the distance from the center of the mass, whereas altitude is altitude, right? R is equal to the radius of the planet plus the altitude. So in altitude questions, you need to say, this is where things get confusing as well, because it can say a satellite is at an altitude of something. You need to be sure if they've accounted for the radius of the planet as well, because that's a case where a lot of people end up making calculator errors as well. Their method could be right, but they forget to add the radius of the planet as well. And that could be a place where a lot of people lose marks as well. But yeah, we can now move on to gravitational potential energy. So all these definitions, they could be tested in like 1 to 2 markers. So yeah, just make sure you know the content, right? So gravitational potential energy is the energy possessed by an object when it is raised in a gravitational field. And what we need to know about this is GPE always holds a negative value. That is because GPE originates or is at or equals 0 or originates at some point infinitely far away. And so the further away we get from it, the more like we're negative, right? So we're in the negative values. And so because we're talking about gravitational potential energy being 0 at a point infinitely far away from the point that we're measuring from, we will always be in a, like GPE will always hold a negative value. That doesn't mean that the change in GPE is different, because a change in GPE can be positive, but GPE standalone can hold is always a negative value. So we have now two formulas, right, that we should know: escape velocity and orbital velocity. I'd recommend in your questions deriving these formulas, because I don't think it's in your data sheet. So if you have a formula in your data sheet, you don't need to derive it. If it's not in your formula sheet, then you would have to derive it, because it's not considered like known, like pre-known content. So with escape velocity, if we're gonna derive the equation, we can let energy initial equal energy final, right? Because there's conservation of energy. So what we'll do is we'll break it down. So we have initial gravitational potential and initial kinetic, so U plus K, and initial and final gravitational potential and final kinetic, right? Let's think about what escape velocity means. Escape velocity is the minimum velocity required for an object to escape the gravitational field of the thing that it's trapped in, right? The minimum velocity required. So at that minimum velocity, because it's minimum velocity, as it like reaches the very end of, as it's like finally escaped, right? Because it's minimum velocity, the moment it escapes the gravitational field, it will basically run out of speed, right? Because it's the minimum velocity required, so that it will use up all of its energy to basically leave the field. And because of that, we can say kinetic energy is 0, because after it leaves the field, it will stop moving, because it's the minimum energy required. So half mv squared is equal to 0. Same way, we can also say GPE is also equal to 0, because when we've escaped the gravitational potential field, that basically means we have reached that point that is infinitely far away, that point where GPE equals 0. And so we can say now our final E is equal to 0. So now we have energy initial. So we have half mv squared is equal to minus gmm over r. So we have half mv squared is equal to gmm over r. So solving that formula now, we can do v squared is equal to 2gm over r, and we will get our escape velocity value as v equals root 2gm over r. So that is our value for escape velocity. And we can also solve orbital velocity. So what will we do when we're solving orbital velocity? Well, if you think about the setup for orbital velocity, we're just like in orbital velocity, it's not always uniform circular motion, like it's elliptical, like the Earth will orbit the sun in an elliptical orbit. But for the sake of the equation, we're going to consider it as uniform circular motion. So if that planetary, or like if that object is undergoing uniform circular motion over the planetary body, then that would mean that there will be a centripetal force, right? Centripetal force in this case would act perpendicular, right? And if it's acting perpendicularly, it will basically be acting downwards, right? Downwards towards the center of the Earth. The only other force that acts downwards towards the center of the Earth that we currently know of is gravity. So in this, if to solve orbital velocity, what we do is we let the centripetal force equal to gravitational force, as you can see over here. So we have mv squared over r is equal to gmm over r squared. So we have v squared is equal to gm over r, and then we have v is equal to root gm over r, sorry. So escape velocity, v is equal to root 2 gm over r, and v is equal to root gm over r. This is another reason why I recommend that you guys aim to derive the formulas, because you can get confused. So because these two formulas are pretty similar, you can end up getting confused. But if you derive them, then you generally have an understanding of where the formulas come from, and you're also able to explain that understanding and show that understanding in your answers as well. So yeah, basically the total energy is equal to U plus K. So total energy in this sense can be calculated by U plus K, which will be equal to negative GMM over 2R. Negative GMM over 2R. The change in energy between orbits is equal to final energy minus initial energy. Increasing orbit equals positive work, which equals positive change. Decreasing orbit equals negative work, which equals negative change. So for this question, for the question U plus K, we will use our value for we'll use our known value for velocity, which will be orbital velocity in this case. So yeah. But all right, we can now move on to satellites now. So with our understanding of satellites, we have satellites are basically projectiles in space orbiting the Earth in circular motion. So we have two types of satellites. We have LEO, lower Earth orbit satellites, which orbit at a low altitude of around 200 to 2,000 kilometers, right? And this places it above the denser part of the atmosphere. And by placing it above the denser part of the atmosphere, what we're doing is we're reducing drag. And so that kind of helps the satellite stay in orbit for longer. And if you think about the orbital period of the LEO satellites, it has an orbital period of less than 128 minutes. And so these are some of the properties. So in terms of explaining questions about satellites, you need to think about the properties and then relate the properties to its uses. So it's got a low altitude. It's got its main feature is the fact that it's got a low altitude, right? And because it has a low altitude, it's pretty good for communications, reconnaissance, and imaging. So Earth observation as well as reconnaissance, those are some pretty good uses for lower Earth orbit satellites. We also have geostationary satellites. So geostationary satellites orbit at around 36,000 kilometers, an altitude of around 36,000 kilometers. And you can see what's special about it because it's part of the name. They are stationary. They appear stationary in the sky, right? So they're not stationary themselves, but they appear stationary in the skies because they have an orbital period of around 24 hours. So it has the same orbital period as that of the Earth. And so it will appear to be stationary exactly one spot above the Earth. So because of this feature now, because of this feature, they will be used for a variety of things, such as communication and broadcasting satellites. So communication, the reason why it's used for communication is because they're so high, they can cover such a wide area of the Earth's surface, and so they're pretty useful for communication. In terms of broadcasting satellites, right? If you think of satellite dishes, or just those like receiving dishes, right? if your satellite appears stationary in the sky, then those receiver dishes only need to point to one fixed position in the sky, right? They don't have to move around as the Earth orbits or as the satellite moves. So it's very useful in that case as well.